Friends, today we are exploring the graphs and planar graphs which form the fifth chapter of our course in discrete mathematics. The basics of multigraphs, weighted graphs, paths and circuits are discussed in this session. Two important types of graphs, namely the Eulerian and the Hamiltonian graphs, are introduced. Also, it includes simple applications like the shortest path problem, the travelling salesman problem and the Euler's theorem, which has great geometrical importance. Graphs and planar graphs. Introduction. It is believed that graph theory had its beginning when Euler in 1736 solved an interesting problem which is now known as the Königsberg bridge problem. In the village Königsberg, there flows a river and there are 7 bridges across it connecting the 4 land portions as shown in the picture. The problem was to start from any one of the land portions and to return to the starting point by walking exactly once over each bridge. This problem was a fascination to many. Thousands of them tried again and again, but no one succeeded in the game. Euler put an end to everyone's anxiety by proving the impossibility of such a walk. As a consequence, graph theory, an interesting branch in mathematics, was evolved. Basic terminology. A graph or digraph is formally defined as an ordered pair VE, where V is a set of points called vertices and E is a set of pairs of elements of V. Elements of V are called edges. A directed graph or digraph is formally defined as an ordered pair VE, where V is a set of points called vertices and E is a set of ordered pairs of elements of V. Thus, the set E of edges is a relation on the set V of vertices. If the ordered pair Vi Vj represents an edge, then we say that Vi is the initial vertex and Vj is the terminal vertex. Here, the edge is said to be incident from Vi and incident into Vj. Moreover, the vertices Vi and Vj are said to be adjacent. If the initial and terminal vertices coincide, then the edge is called a loop. If E is taken as a multi-set of pairs of elements of V, then the graph is an undirected graph. If a pair is repeated in the multi-set, then the graph is said to have multiple edges. The concept of undirected graphs can be made clear by considering the different places and roads connecting them. The vertices are places and the edges are roads. It is possible to have more than one road connecting two given places. Similarly, when we consider a geographical map, the adjacent regions will be shaded by different colors. Such a map can be represented by a graph by marking the different regions as vertices and edges stand for the adjacency of the different regions. The schedule of games in a tournament also may be taken as an undirected graph. Here, the different players form the vertices and an edge signifies a game played between the two players representing the vertices. In the following undirected graph, the vertex set is V equals set of all elements V1, V2, V3, V4, V5 and the set of edges is E equals set of all ordered pairs V1, V2, V2, V5, 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 V4, V5, V4, V5. There is a loop connecting the vertex V5 to itself and there are multiple edges between the vertices V4 and V5. Consider the following graph. It has a loop and multiple edges. In this graph, the edges are given names. The set of edges is E equals set of all elements E1, E2, E3, E4, E5, where E1 is the edge connecting the vertices V1 and V2. There is a loop at the vertex V5 which is given by the edge E3. There are two edges, that is multiple edges, which are E4 and E5 between the vertices V4 and V5. A graph having neither loops nor multiple edges is called a simple graph. For such a graph, the number of vertices adjacent to a vertex is called the degree of the vertex. From the definition, it is clear that the sum of degree of all the vertices will be twice the number of edges. In other words, the sum of degree of all the vertices is an even number. This is a useful observation in the theory of graphs. In a directed graph, as the edges can be observed from two different directions, the degree can be described in two types. They are the in degree, that is the number of edges incident into the vertex, and the out degree, that is the number of edges incident from the vertex. Sometimes weights or numerical values are assigned corresponding to the edges. For instance, in a graph representing places and the connecting roads, the distance between two places along a road may be seen as the weight of the corresponding edge. Such graphs are called weighted graphs. A simple graph in which any two vertices are adjacent is called a complete graph. A complete graph on n vertices is denoted by Kn. Suppose a graph is given with V as the vertex set and E as the edge set. When we consider a subset W of V, naturally we may restrict our attention to only those edges in E connecting the vertices in W. The resulting graph is called a subgraph of the given graph. A subgraph of a graph is called a spanning subgraph if it contains all the vertices of the graph. For a graph on n vertices, we can find a new graph on the same vertex set such that two vertices in the new graph are adjacent if and only if they are not adjacent in the given graph. In other words, the two graphs have the same set of vertices. The new graph, called the complement of the graph, contains only those edges in Kn that are not in the given graph. The complement of a graph G on n vertices with respect to the complete graph Kn is denoted by G, which equals Kn difference G. We can have the complement of a subgraph with respect to a graph also. Let G dash equals pair V dash E dash be a subgraph of a graph G equals pair VE. Another subgraph pair V double dash E double dash is called the complement of pair V dash E dash if E double dash equals E difference E dash and V double dash contains only those vertices with which the edges in E double dash are incident. A graph whose vertex set V is the union of two disjoint sets V1 and V2 such that any edge is a join of vertex in V1 and a vertex in V2 is called a bipartite graph. If the sets V1 and V2 have m and n vertices respectively, and if every vertex of V1 is joined to every vertex of V2, the graph is called a complete bipartite graph and it is denoted by Kmn. The following figure represents the complete bipartite graph K23. Paths and circuits. In a directed graph, a sequence set of all elements E1, E2, etc. En of edges with the terminal vertex of Ei and the initial vertex of Ei plus 1 coincide for 1 less than or equal to I less than or equal to n minus 1 is called a path. If none of the edges appear more than once, the path is said to be simple. If no vertex appears more than once, the path is said to be elementary. A path set of all elements E1, E2, etc. En in which the initial vertex of E1 and the terminal vertex of En coincide is called a circuit. A circuit in which none of the edges are repeating is called simple. If none of the vertices are repeating, the circuit is called elementary. We can as well describe the paths and circuits as sequences of vertices and edges. We have a theorem which states that in a graph with n vertices, if there is a path from vertex V1 to vertex V2, then there is a path of no more than n minus 1 edges from vertex V1 to vertex V2. Proof: suppose there is a path from V1 to V2. Let set of all elements V1 etc. Vi etc. V2 be the sequence of vertices that the path meets when it is traced from V1 to V2. If there are m edges in the path, there are m plus 1 vertices in the sequence. For m larger than n minus 1, there must be a vertex Vk that appears more than once in the sequence, that is, the sequence will be set of all elements V1 etc. Vi etc. Vk etc. Vk etc. V2. Deleting the edges in the path that leads Vk back to Vk, we have a path from V1 to V2 that has fewer edges than the original one. This argument can be repeated until we have a path that has n minus 1 or fewer edges. Note, the theorem says that the maximum length of an elementary path in a graph having n vertices is n minus 1. Shortest path in weighted graphs. A weighted graph can be considered as a triple G equals triple V E W, where V is the set of vertices, E is the set of edges, and W is a real valued function whose domain is E. If U and V are two vertices, then W of UV denotes the weight of the edge joining U and V. For two non-adjacent vertices A and B, the sum of weights of the edges in the path is called the length of the path, and it is denoted by L of AB. For any pair of vertices of the graph, the shortest path problem requires to find that path joining the given two vertices along which the length is the minimum. For instance, if a weighted graph represents many cities connected by roads and the weights as distances along these roads, then the problem asks one to find a path along which the distance is the least. Instead of distances, if the weights represent the expense for travel, then the problem asks one to find the path making the least expense. There are several algorithms available to determine the shortest path joining a given pair of vertices in a graph. The following algorithm is the one discovered by E.W. Dijkstra, which is used to find the shortest path from a vertex A to another vertex B in a directed or undirected graph G. Step 1. Start with L of A equals 0 and L of V equals infinity for all other vertices V. Step 2. For all vertices V which are adjacent to A in an undirected graph or which are incident from A in the directed graph, find the minimum of L of A plus W of AB. Let X be the vertex corresponding to this minimum. Then replace L of A with L of X equals L of A plus W of AX. Step 3. Now find the minimum of L of V for all vertices U in step 2 and L of X plus W of AU, where U is a vertex adjacent to X. Step 4. Continue the steps 2 and 3 till we reach the vertex B. Example. Let us find the shortest path from the vertex labeled as 1 to the vertex labeled as 5 in the given directed graph. When we follow the steps of the algorithm, as the first step, we fix L of 1 equals 0 and L of V equals infinity for all other vertices of the graph. The vertices to which we can reach from 1 are 2, 3 and 6. We calculate the lengths of the corresponding paths as L of 2 equals L of 1 plus W of 1 2 equals 7, L of 3 equals L of 1 plus W of 1 3 equals 9, and L of 6 equals L of 1 plus W of 1 6 equals 14. The minimum value is L of 2 equals 7. So we temporarily reach the vertex 2 in the second step. Now we go to the third step. We can reach the vertices 3 and 4 from 2. So we calculate L of 3 equals L of 2 plus W of 2 3 equals 7 plus 10 equals 17, and L of 4 equals L of 2 plus W of 2 4 equals 7 plus 15 equals 22. But 3 is reachable directly from 1 in the second step with a weight of 9. The minimum of the values 9, 17 and 22 is 9. So, we temporarily fix the direct path from 1 to 3. Thus, at the end of the third step, we are at the vertex 3 and L of 3 equals 9. Now we go to the fourth step. The vertices to which we can reach from 3 are 4 and 6. So, we calculate L of 4 equals L of 3 plus W of 3 4 equals 9 plus 11 equals 20 and L of 6 equals L of 3 plus W of 3 6 equals 9 plus 2 equals 11. The vertex 6 was directly reachable from 1 with a weight of 14. The minimum of the values 11, 14 and 20 is 11. So, we temporarily fix the vertex 6 and the path 1 to 6 through 3. Now we go to the fifth step. The only vertex to which we can reach from 6 is 5. So, L of 5 equals L of 6 plus W of 6 5 equals 11 plus 9 equals 20. Since there is an edge from 4 to 5 which we could have chosen after the second step, we can also have L of 5 equals L of 4 plus W of 4 5 equals 22 plus 6 equals 28. Clearly, the minimum value among these two is 20, which is taken as the length of the path from vertex 1 to vertex 5 through the vertices 3 and 6. Thus, the algorithm is completed and we get the shortest path from 1 to 5 as 1 to 3, 3 to 6, 6 to 5, which has a total length 20. A graph is said to be disconnected if the vertex set is the union of pairwise disjoint subsets and any edge of the graph is a join of two vertices both belonging to any one of these subsets. A graph is said to be connected if it is not disconnected. A connected subgraph of a graph is called a component of the graph. Eulerian paths and circuits. The Coinsberg bridge problem led to the Eulerian graphs in which it is possible to have a path joining any two vertices such that no edge is repeated. If the initial and terminal vertices coincide, the circuit is Eulerian. In this direction, there is a theorem due to Euler. The theorem states that an undirected graph possesses an Eulerian path if and only if it is connected and has either no vertices or two vertices of odd degree. The following corollary is useful. The corollary states that an undirected graph possesses an Eulerian circuit if and only if it is connected and its vertices are all of even degree. Now, let us look at the graph representing the Coinsberg bridges. All the four vertices of it have degree 3. So, by the corollary, the graph corresponding to the Coinsberg bridges cannot have an Eulerian circuit. Hamiltonian paths and circuits. A path or circuit in which no vertex of the graph is repeated is called a Hamiltonian path or circuit. Consider the problem of seating a group of people around a table. If we let the vertices of an undirected graph denote the people and the edges represent the relation that two people are friends, a Hamiltonian circuit corresponds to a way of seating them so that everyone has a friend on each side. The following theorem assures a sufficient condition for the existence of a Hamiltonian path in an undirected graph. The theorem states that let G be a graph on n vertices. If the sum of the degrees for each pair of vertices in G is n minus 1 or larger, then there exists a Hamiltonian path in G. Example: consider the problem of scheduling 7 examinations in 7 days so that 2 examinations given by the same instructor are not scheduled on consecutive days. If no instructor gives more than 4 examinations, show that it is always possible to schedule the examinations. Let G be a graph with 7 vertices corresponding to the 7 examinations. There is an edge between any two vertices which correspond to 2 examinations given by different instructors. Since the degree of each vertex is at least 3, the sum of the degrees of any two vertices is at least 6. Consequently, G always contains a Hamiltonian path which corresponds to a suitable schedule for the 7 examinations. We have a theorem which states that any directed complete graph contains a Hamiltonian path. The proof of this theorem is trivial. As an illustration of it, consider the following example. Let us consider the problem of ranking players in a round-robin tennis tournament such that player A will be ranked higher than player B if A beats B or A beats a player who beats B, and so on. Since the outcomes of the matches can be represented as a directed complete graph, the existence of a Hamiltonian path in the graph means that it is always possible to rank the players. This ranking need not be unique. We introduce a problem similar to that of the shortest path problem. It is known as the travelling salesman problem. Let G equals triple VEW be a complete graph on n vertices where W is a function from E to the set of positive real numbers such that for any 3 vertices Vi, Vj, Vk in V, W of Vi Vj plus W of Vj Vk greater than or equal to W of Vi Vk. Here, W of Vi Vj stands for the weight of the corresponding edge. The problem asks for a Hamiltonian circuit of minimum length. Suppose a salesman has to visit many customers at different places and has to return to his place. Suppose there are roads connecting these places. The problem is to determine the shortest route which he must follow to visit all these customers such that no one is visited more than once. It is possible to find such a circuit. The method is similar to the one we followed in the shortest path problem. Planar graphs. This forms an important type of graphs. A graph is said to be planar if any pair of edges meet only at some vertex. In other words, there are no crossovers of edges in the graph at points other than vertices. In this context, we introduce the concept of an isomorphism between two graphs. Let G equals pair VE and G dash equals pair V dash E dash be two graphs. Let phi from V to V dash be a bijective function such that phi of Vi and phi of Vj are adjacent in G dash if and only if Vi and Vj are adjacent in G. Isomorphism permits a renaming of the vertices of one graph to get the other so that neither an existing edge is lost nor a new edge is created. Two isomorphic graphs need not look alike, but the adjacency of vertices will be preserved. This is shown in the figure. Planar graphs become useful in the design of electronic integrated circuits due to the following reasons. In an integrated circuit, there must not be any crossover of wires other than at terminals. Moreover, the number of vertices increases according to the complexity of the task to be performed. A planar graph divides the plane into non-overlapping regions or faces. The number of faces in the graph shown is 4. The first graph seems to divide the plane into 5 regions. But to get the actual number of regions, we consider its isomorphic graph having no edge crossing at non-vertex points. So it follows that the number of regions is only 4. Planar graphs have interesting geometrical properties also. The following theorem due to Euler is one of the most popular one in graph theory. The theorem states that in any connected planar graph, V minus E plus F equals 2, where E, F and V are respectively the number of edges, number of faces and number of vertices. The equation in the theorem is called the Euler's formula. A graph that does not satisfy the Euler's formula will be non-planar. Kuratowski's theorem gives a characterization for planar graphs. The theorem states that a graph is planar if and only if it does not contain a subgraph isomorphic either to K5 or to K33. Let us summarize the contents of this session. Graph theory was introduced giving an emphasis to the historical background and some of the important applications. The important types of graphs, namely Eulerian and Hamiltonian graphs, were introduced and their applications in real-life situations were discussed. Planar graphs, another important type of graph, was also introduced. Besides these, some of the important theorems also were stated. The following questions are provided for testing yourself. First, prove that the sum of degree of vertices of a graph is always an even number. Next, draw two non-isomorphic graphs on 3 vertices. Next, draw K5 and mark an Eulerian path in it. Next, a graph is self-complementary if it is isomorphic to its complement. Give example of such a graph. Next, draw K23 as a planar graph. Verify the Euler's formula in it. The following books are suggested for further reading. Elements of Discrete Mathematics by C. L. Liu, Tata McGraw-Hill Publishing Company, 2nd edition. Introduction to Graph Theory by Robin J. Wilson, 4th edition, Addison Wellesley Longman Limited. Graph Theory with Applications by J. A. Bondi and U. S. R. Murthy, American Elsevier. Discrete and Combinatorial Mathematics, an Applied Introduction by Ralph P. Girmaldi, Pearson Education, 4th edition. Hope you have followed this session. We will continue our discussion with trees and cut sets in the next chapter. Till then, goodbye.